Hi, I'm Dr. Michail Stamatakis, and in this lecture we will touch upon the fundamentals of kinetic Monte Carlo simulations of surface reactions. So let's start with a little bit of motivation and answer the question, why do we care about kinetic modeling in fields like catalysis and surface science? So in the course we have seen quite a lot about DFT calculations, and in the context of catalysis we use density functional theory to investigate the electronic structure of the material, namely our catalyst, also investigate the stability of intermediates, so adsorbates that bind to the catalytic sites, and also intermediates, namely species that may be produced by elementary reactions between these adsorbates. So we can use DFT to find the absorption energies or the formation energies of these intermediates, and then we can do calculations to find also the transition states of the elementary events that gives rise to these intermediates, thereby making statements about the chemical pathways, the possible chemistry that can take place on the surface of the catalyst, and then by calculating the energy barriers, we can make some qualitative predictions about which kind of reactions might be more prominent on the surface of the catalyst. However, if we need some sort of predictive approach, and we may need predictive models for capturing trends in activity and selectivity of catalytic materials. So if we have this kind of need, then things are a bit more complicated. We may be dealing with parallel or competing pathways. So it may not be as simple as looking at an energy landscape and saying this is the prominent pathway. There may actually be competing pathways which give rise to different products, some of which may be more desirable than others. Some products may even be completely undesirable because they may result to poisoning, for example. So this source of complexity gives rise to considerations about, for instance, the selectivity of our catalytic material. Now, of course, especially if we have competing pathways, temperature and pressure may exert an influence on which pathway might be dominant. So, and actually the dominant pathway may not be the same if we carry out the reaction at a certain set of conditions versus another set of conditions. Finally, we may have some complexity because of coverage effects on the reaction rates. So if we have reactions that happen on the surface of the catalyst, this adsorbate layer, which is also referred to as the add layer, is essentially a condensed phase. So a reaction that happens in the presence of several spectator species is going to have a different rate than the same reaction happening in the absence of any spectators. So this is what we refer to as coverage effects. And these can be quite prominent. So in order to incorporate all of these sources of complexity in a modeling approach that is predictive, we can do something like kinetic Monte Carlo calculations. So in any case, we need some sort of kinetic modeling approach to tackle all of these issues, these sources of complexity. So in this lecture, we will focus on the kinetic Monte Carlo approach for kinetic modeling. And you may be wondering, why not do some sort of ab initio molecular dynamics? So I'm going to answer this question by looking into a very simple sort of model system, a model elementary reaction in which we have CO at the gas phase interacting and reacting with the hydroxyl species on the surface and giving us this species here, carboxyl. So if we were to do a calculation of the energy of the system for several different configurations, so the configuration in this case is the position of the atoms in the three-dimensional space, we would see something that looks like this. This is the well-known potential energy surface concept. So the energy for the specific configuration. So in the potential energy surface, we would see some minima that correspond to stable reactants or products, in any case, stable species that our atoms can make. And we're going to also see that these are separated by some barriers. So this is a static picture. If we wanted to do some ab initio molecular dynamics, we would see something that looks like this. So after a wandering around the reactants region, we cross this barrier and we go into the products region. So now we are here in this configuration. Of course, this plot is just an idealization. You can imagine this potential energy surface being a multi-dimensional thing, right? There is a high dimensionality of this, but the point is the same. We would have some minima, and then the reaction would essentially be a barrier crossing event. Now, the problem with molecular dynamics is that we would have to spend quite a lot of computational effort in resolving all these atomic vibrations as we are wandering about the reactants region, up to the point that we get enough energy to cross that barrier. So barrier crossing is actually a very, very rare event. So if we were to do a calculation with molecular dynamics, a flavor of ab initio molecular dynamics, it would be quite computationally expensive. And if we wanted to simulate several reactions and several different types of reactions in order to go to the overall pathway, chemical pathway simulation, then this would simply be infeasible. However, instead of simulating dynamics, we can do something else. So we can use the kinetic Monte Carlo method, which focuses on rare events. So here is what the kinetic Monte Carlo would do. The KMC approach doesn't really care about resolving all these atomic vibrations in the reactants region, etc. It cares about an average rate of crossing this barrier, and this average rate, also referred to as the propensity, can be computed if we know the rate constant for our reaction. So here is the expression of the rate constant from transition state theory. We're going to talk about transition state theory in more detail later in the presentation. So the point here is that all of these constants, so all of these terms here, are either constants, right, like Kb, the Boltzmann constant, H, the Planck's constant, the temperature here, etc. So they're either constants or can be calculated from a density functional theory, or in any case, any lower level calculation. So these are quasi-partition functions for the transition state and the reactants. This is the activation energy. So this would be the potential energy of the transition state minus the potential energy of the reactants, etc. So the only thing that we would not be able to calculate with static DFT calculations is this transmission coefficient that really requires dynamics. But this one, we usually take it equal to 1. We just neglect it. So to a good approximation, we can just use this part for the rate constant of the reaction. So then, if we have the rate constant of the reaction, it becomes possible to generate random numbers which correspond to the random times in which we're going to cross the barrier. So this is what kinetic Monte Carlo does, and of course in this lecture we're going to discuss this in more detail and see what kind of components we need for the simulation. So we end up simulating reactions much faster than molecular dynamics because we don't have to resolve all these atomic vibrations, and at the same time kinetic Monte Carlo incorporates, or rather retains, the spatial information. So in the kinetic Monte Carlo approach, we can tell which adsorbate is sitting on which site, right? So you still have the spatial information, contrary to microkinetic models, which are differential equations for the coverage of the adsorbates. So for these microkinetic models, you don't have any spatial information. You only care about the average coverage of an adsorbate on the overall surface. So there are quite a few advantages, as we see, of the kinetic Monte Carlo, which is going to be the main topic of this talk. So for the rest of the lecture, we're going to discuss some concepts at the atomistic and molecular level, specifically transition state theory and how we can calculate rates of elementary events using this theory. Then we're going to transition to the mesoscopic level. So we're going to discuss the simulation of reactions on spatially extended systems, like this nanoparticle here, which we represent as a lattice in the kinetic Monte Carlo approach. And finally, we will discuss some more advanced topics on the accurate modeling of catalytic surface reactions, dealing with complex materials, like this one, for example, complicated reactions that may involve species that bind to more than one site, and also specific geometric arrangements of the reactants and the products, different site types, etc. And finally, we're going to discuss in this context the effect of coverage on reaction rate. So let's start with the transition state theory fundamentals. I'd like to point out early on that transition state theory is an equilibrium theory. It assumes that quasi-equilibrium has been reached between the initial state and the transition state. Now, the transition state is a thin region of the space which has dimensionality equal to the dimensionality of our overall space minus 1. So it's really a dividing surface that, or hypersurface, that separates reactants from products. So here are our reactants in the potential energy surface, again, A plus B. This is the transition state region, right? This thin slice of space, this hypersurface. And here are the products, C plus D. So the overall process would be a reaction that gives us from A to B, gives us the product C plus D, but this happens through, of course, the transition state. The system has to go through this dividing hypersurface in order to get to the product region. So we're going to denote this as with this notation here. So A plus B is quasi-equilibrated with the transition state. And then the transition state goes into C plus D. And of course, for our investigations, we will assume that this is quasi-equilibrated. Of course, if we want to calculate the reverse rate from transition state theory, then of course this will have to also be quasi-equilibrated. So by assumption of this quasi-equilibrium, we can write our first important equation that we will use in deriving the final formula of the rate constant from transition state theory. So this equation basically says that the concentration of activated complexes, right? So the transition state type of configuration. So this concentration divided by the product of the concentrations of the reactants is simply equal to the partition function of the transition state divided by the product of partition functions of the reactants. So we can write these partition functions. We use classical statistical mechanics in our derivations. So we use this is supposed to be the classical Hamiltonian containing momentum and the potential energy contribution for reactant A. So this formula we have seen before. We denote the phase space with gamma A, right, for species A over here. And remember that we have this H, which gives us the approximate count of quantum states and also makes the integral non-dimensional. Now, A and B are supposed to be non-interacting with each other when we are at the reactant configuration. So we write a similar equation for the partition function of B. Now what about the transition state? In the transition state, the atoms of A and the atoms of B are close to each other and they're actually interacting. So in the transition state, we write a similar equation which has which pertains to all the atoms of the reactant molecule and the product molecule. So you will notice that we have this h raised to the 3n power here, where n is the sum of the number of atoms of A and B. H star is the Hamiltonian of the system, of the interacting atoms, and the integration is happening at this thin region, right, of the space, which is essentially this corresponds to the transition state region, this thin part of the space. Now, we already know the expressions of the Hamiltonian for the reactants, reactant A and reactant B. So, if you remember from the previous lecture, we said that these Hamiltonians can have translational, rotational, vibrational contributions, and we know how to calculate the quasi-partition functions for each one of these contributions. So we can relatively easily find the partition functions of the reactants. But what about the transition state? So in the transition state region, we notice that we have this kind of bump over here, right? So we have this negative curvature along the, as we call it, the reaction coordinate, right? So how are we going to deal with this? Essentially, we're going to assume that the Hamiltonian of the transition state has two contributions. One contribution is kinetic energy along the reaction coordinate. So when the system approaches this point, it will have some momentum, hopefully momentum to bring it towards the products region, but not always. It may go up to close to the transition state and come back. So this would be kinetic energy, right, because of that momentum. So kinetic energy along the reaction coordinate. Then we have this H double dagger, which is pretty much everything else. So this everything else will include the energy contributions because of, for example, rotations or vibrations or other translations in any other coordinate except the reaction coordinate. Right. So we took the kinetic energy along the reaction coordinate out of this. So we have now the Hamiltonian of the transition state expressed as this term plus the everything else term. Now we can substitute this H star into the equation that we discussed a moment ago. And if we do that, we are going to, of course, have a couple of terms here, right? One term because of this. This is this term over here. And then the other term over this, which basically now this has to be integrated in the in a space which corresponds to this gamma double dagger, all the other degrees of freedom. So now this is our partition function for that part. And in this case, I have also broken down this h to the 3n. So this is h to the 3n minus 1 times h. And then notice that the integral along the spatial coordinate, the reaction coordinate, from here is going to give me a factor of delta that is coming out of the integral over there. So this is the equation that we get from this part, and then of course we have this Gaussian integral, which comes from the kinetic energy part. Now there is a bit of a slight problem here, as you may notice, because this delta is not a very well defined parameter. right? So the delta is the thickness of the transition state region. But you will see later that this delta will get eliminated at a later stage of this derivation. So we will keep it here because this is this term actually arises, as we said, from this integral. But don't worry too much about this. It's going to be eliminated at a later stage. Now we can denote all this blue term as Q double dagger. And this is actually a well-defined thing, right? Because we can integrate this expression along this thin region of space. This is fine. So this is a well-defined thing. The only problematic term is this, which will be eliminated. Now, this term here, we know, we have seen similar terms before. We have treated similar integrals. So this is simply this square root of 2 pi m star times kBt. M star is the reduced mass of the system, which is a function of the masses of the reactants here. Next, we need to make a statement about the number of transitions from reactants to products per unit time. So this, on average, is equal to the rate of from transition state theory times dt. So this would be the average number of transitions, reactive transitions, within a differential time interval, dt. And this is simply equal to the rate constant from transition state theory times the concentration of reactant A times the concentration of reactant B times dt. So we're using the standard mass action law formulation because this event is assumed to be an elementary event. So this is equal to this expression over here. So let's try to see how this came about. There are, well, two main ingredients or terms in this product. The concentration of the activated complexes times all this, which is indicative of the rate. It gives us the rate with which an activated complex transitions towards, moves towards the products region. So let's try to analyze this expression. And to do that, I would like to draw your attention to this schematic here. So this is basically a magnified sort of close-up, right? It's a close-up of this area over here. So we're sitting on top of the transition state, right? So this is our delta, the thickness of the transition state. The reaction coordinate is along this direction. And this is the probability that we find our system in the transition state region. So this probability moves with some velocity towards the products region. So I'm showing this velocity vector here, right? It's momentum divided by the mass of our system. So the velocity is this, and then the delta x that I'm showing here is basically the velocity times delta t. So at time equals 0, then this blue rectangle would be indicative of the probability that we reach the transition state at the transition state region at that time. And then at the next time step, delta t dt, then this thing has moved a little bit. By how much? By delta x. So this is really the probability outflux, right, that goes towards the products region over here. So if I calculate this, the fraction between this and what I had in the transition state region at time equals 0, then this is giving me the portion of the portion of systems in my ensemble in which a reactive transition has happened, because I was in the transition state region. Now here I'm in the products region. So let's look at that. Here is the term P over the reduced mass times delta T, right? So this is this is really my delta x that I see here. Delta x divided by delta, right? So delta x divided by delta is the fraction of systems in my ensemble that undergoes the reactive transition. And then I note that this momentum is not just one value, it is really a distribution, right? So by the quasi-equilibrium assumption, we can use the appropriate Maxwell-Boltzmann distribution for the momentum, and this is really what this term gives me, basically this term divided by that, right? So this is the probability factor that I will have momentum P in my system, and then this is the corresponding partition function for that momentum. So this e to the minus p squared divided by all this divided by this gives me the probability that my momentum will have value p. So if I do the integration, then I account for all the possible different values of the velocity at equilibrium, of course, at thermal equilibrium. So then this whole thing, as I said, this is fraction of systems, basically a fraction of activated complexes that go towards the product. And then I also take into account the fact that P is a distribution. So overall, all of this thing is going to give me exactly what I want, the number of reactive transitions per unit time. So now we have to treat these integrals. So this is a Gaussian integral, right? It gives rise to this term over here. This, if you think about it, is really the mean of the Gaussian distribution. So this could give rise to the remaining terms over here. So then in the end, I end up with this equation. The reduced masses cancel out, and here is this delta parameter again, which will be eliminated with the other delta that we had in the first equation that we derived. So let's now collect all the important equations that we derived, the ones that I put in red boxes. Right, so basically this is not an equation, this is a term, but the equation is that this is equal to this term over here. So here we summarize the equations in the red boxes. This one was derived first early on when we talked about the quasi-equilibrium assumption. So this gives us a way to calculate the concentration of the activated complexes versus the concentrations of the reactants, right, with respect to the partition functions. Then this equation came up when we made the assumption about the Hamiltonian of the transition state. We broke it into a kinetic energy contribution along the reaction coordinate and then everything else. So this is the quasi-partition function for everything else. And this came from the kinetic energy. And finally, this is the equation that we just discussed a moment ago in the previous slide, which was derived when we started counting the average number of reactive trajectories per unit time. So what can I do? I can basically, what I want is KTST. So I can substitute this with this, and then this Q star can be substituted by this. You will immediately see that this delta with this delta go away. Remember, this was not very well defined parameter, so it goes away, it's eliminated now, so we have no problem. And then of course this also goes away with this. So in the end I derive a very simple equation which gives me the transition state theory kinetic constant with respect to the partition function of the activated complex versus the reactants, and I also have this KT over H, which is sometimes referred to as the thermal factor. So if I know some properties of these molecules, and I also know my temperature, then I can find the average rate from this transition state theory approximation. Now, you may have seen slightly modified versions of this. First of all, sometimes we take into account this fudge factor, which accounts for recrossings. Recrossings happen when a system goes up to the transition state, but then doesn't cross. It goes back into the reactance region, doesn't cross to the products region. This is a difficult factor to calculate. You need dynamic simulations to estimate its value. So this is shown here. And then the potential energy contribution sometimes is taken out of the partition functions, out of these. So then you would write something like this. So Q lowercase, which is a quasi-partition function that does not account for the potential energy contribution, divided by Q reactants. So this would be just the product, right? You can imagine this being a lowercase qa times lowercase qb. Again, this would not take into account the potential energy. So the potential energy is taken into account in this exponential term. So e to the minus activation energy, which is the potential energy of the transition state minus the potential energy of the reactant configurations, divided by kBt over there. So this is equivalent to that in the case where kappa is equal to 1, of course. And you may also have seen other equations in which these go, they get combined with this, so you have e to the minus some sort of free energy difference between transition state minus reactants, etc. In other textbooks, you may have seen pre-exponentials that contain entropic contributions, whereas this contains enthalpy contributions, etc. But these are all versions of the same fundamental equation, this equation that comes from transition state theory. So what does it all mean and why is it useful? We have derived this K, the rate constant of the reaction, using transition state theory approximations. So the rate with which we transition from reactants to products per unit time is equal to this expression over here. Now, what about the statistics of these transitions? So when we talk about statistics, it's useful to introduce an ensemble. So this would be a collection of systems in which we start the system from different points of the reactants region, and also with different velocities potentially. So if we imagine a collection of such systems, the question is how much time, or one question we can pose is, how much time do we have to wait until we see a reaction event? So we can make the assumption that the system is memoryless. This is a good assumption because if you start the system from here, it takes quite a long time from the point you started it to see a transition. So to a very good approximation, your system would have sampled quite a lot of the states in the reactants region. So it will essentially lose its memory. So if you want to go more rigorous mathematically, if you want to make more mathematically rigorous statements, then you can say that the correlation times here, or the time scales of the temporal correlation functions, are much, much shorter than the time scales of the transition events. So this means memoryless. So for memoryless systems, there are some mathematical facts that we can invoke. And essentially, one of them says that the waiting time for events that are characteristic of memoryless systems, the waiting time for such events follows the exponential distribution with rate parameter, in this case RTST. So if we go back to the question, how long are you going to wait to see a transition? Well, this time is a random variable which follows the exponential distribution, which is plotted here. So this is the probability density per time, and the probability density is an exponentially decaying function. So sometimes we write this fact in this notation. So this tau, the time that the reaction will happen, follows the exponential distribution with rate parameter rtst. Right. So this means follows. This is not the exponential function. This is just the exponential distribution with rate parameter rtst. So we answered the question about the waiting time. We can pose different questions as well. So we can say, let's fix the time interval of our observation. So now I'm observing the system from time 0 up to time 1 minute. How many events are going to happen during this 1 minute? Again, by invoking some mathematical theorems, we can state that the number of events in a given time interval is a random variable that follows the Poisson distribution with rate parameter rtst. So an example plot of the Poisson distribution is shown here. So this is a discrete distribution, right? So the number of events follows the Poisson distribution with this rate constant. So the probability of seeing, let's say, 5 events in our 1 minute of observation, for example, is equal to 0.17 or whatever, etc. So the probability of seeing too many events, right, like 10 events here, is much, much lower, etc. So all of these are consequences of the memoryless nature of our random process, the reaction occurrence. This brings me to the end of this part. So we talked about calculating reaction rates for elementary events using transition state theory. These are all applicable to the atomistic molecular level. And in the next part, we're going to discuss how to simulate reactions on spatially extended systems at the mesoscopic level.